Next, we'll do a friction example. We talked a little bit about this sort of thing in class, but we'll put lots of details in here now. You need to move a fridge. It has a mass of 115 kilograms. There's a person pushing quite hard. The coefficients of friction are static and kinetic with these numbers. Part A, how hard do you have to push on the fridge? Part A, draw the free body diagram for the fridge. Okay, so for part A, we can draw the fridge as a big rectangle if we wish. You can also represent it as a dot. We know that the earth pulls down on it. That's the weight vector. We know that the kitchen floor holds it up, assuming it's in the kitchen. That's the normal force. We're pushing on it. We push on it in this direction right here. We might call that an applied force or a pushing force. Doesn't really matter. We see that we're pushing it to the right. We could draw it this way on our diagram, but traditionally we put the tails of our forces over here, the tails of the forces on the object. So I'll call that an applied force. The friction opposes the motion. I'm going to call that a lowercase f. I'm not going to specify what kind of friction because we're going to get into the details of that in the next bits. We'll push on it with a certain amount of strength. Once we overcome the maximum static friction, that's when it'll start to move and it'll switch to kinetic. But for right now, we'll just keep it general with F for friction. Okay, what's going out next? Part B, write Newton's second law for the fridge in both the x and the y directions. So we better get our coordinate systems on there, hey? So let's sort out our forces in their components. We've got the normal force, the applied force, that's us pushing. We've got the weight force and the friction force. And then we'll use static or kinetic as appropriate. So the normal force is only in the y direction. The applied force is only in the x direction. It's to the right, so it's positive. The weight is only in the negative y direction. And our friction force is only in the negative x direction. So there are all the components of our forces. We want to write Newton's second law. So the sum of the forces is ma here. The sum of the forces is ma here. So part B, this is also part B, I suppose. Sum of the forces in the x direction is mass times acceleration in the x direction. In the x direction, we've got the applied force, subtract the friction force, equals mass times acceleration in the x. In the y direction, sum of the forces in the y is mass times acceleration in the y, normal minus mg, equals m times 0. Our fridge is not moving up or down vertically, so the acceleration in the y is 0, and minus mg equals 0. So there are our equations in the x and y direction. Part C, find the normal force on the fridge. The normal force is in the y information, so we'll use our y equation and we'll find the normal force. N equals mg. The mass of the fridge was 115 kilograms. Times g, 9.81 meters per second squared. Our normal force has a magnitude of, why don't we just grab the calculator and do that, 115 times 9.81, 1,128 newtons. It points straight up, so that's the positive y direction. So there's our normal force. Okay, part D, now we're getting into some of the details. What is the hardest you can push on the fridge before it starts to move? So before it starts to move is when it is not moving. So we're definitely dealing with static friction. If we want the hardest you can push, so the hardest you can apply the force, then we must be dealing with the maximum static friction. Because if you push less hard, friction is not at its maximum. So the fridge will move if our applied force is greater than or equal to the maximum static friction, And to go with that, if it's moving, AX is greater than or equal to 0. The threshold case, so the point where it just starts to move, is where the applied force equals the static friction. As soon as those two things are equal and the acceleration is 0, that's kind of the flipping point. That's exactly the point, the threshold, when it will just begin to move. Okay, so now we've put our condition. We'll come back to our Newton's second law, and we recognize now that we're talking about static friction, and we mean maximum static friction. So Fs, so we'll write down our equation again, F applied minus F, now we're talking about maximum static friction, is mass times acceleration in the x, which is m times 0, because we're right on that threshold of it just beginning to move. So our applied force is going to be the maximum static friction. We can find the maximum static friction by multiplying the coefficient of static friction with the normal force. Coefficient of static friction was 0.225. Magnitude of the normal was 1128 newtons. So the magnitude of our pushing force then is 254 newtons. 0.225 times 1128, 254 newtons. So the hardest we can push on it before it starts to move is 254 newtons. As soon as our force exceeds that much or hits that much, that's when it's going to start to move. Part E. If we push with this force, then it'll start moving. What'll be the acceleration of the fridge? Okay, so when the fridge moves, that's because our applied force is now meeting the static friction force. Or why don't we even toss in the word overcoming the static friction? As soon as it matches, it will move. If it moves, we all of a sudden switch to kinetic friction. So if we want to find our acceleration, we come to our Newton's second law equation. If we're in motion, this friction is now Fk. You can redraw your diagram if you wish. Here's our fridge. We've got kinetic friction here, normal force here, applied force here, and weight force here. The sum of the forces in the x direction is mass times acceleration in the x. F applied minus Fk is m times ax. Our static friction force is our coefficient of static friction times the normal force equals m times ax. So let's see what numbers we can put in here. So our applied force is the 254 newtons. We can fill that in. 254 newtons. Subtract mu k, that was given in the original information, 0.175, times the normal force, that doesn't change just because it's starting to move, 1128 newtons, equals the mass of the fridge, that was 115 kilograms, times the acceleration in the x direction. Okay, we'd like to solve that and get our acceleration. So let's do this next line next. 254 subtract 0.175 times 1128. 56.6 newtons equals 115 kilograms times ax. That means our acceleration is 56.6 newtons divided by 115 kilograms. So our acceleration is 0.492. It's in the x direction, so we have units and an x hat. So that's what the acceleration will be. Once we get it moving, we'll keep applying that same constant force, and we're going to have this acceleration. It'll be speeding up as it goes to the right. Okay, that's part E. Part F, how long will it take you to move the fridge 15 meters? All right, this is a kinematics problem. So let's do some kinematics here. Part D, so here's our fridge. We'll just do a sketch. There's our coordinate system, x. We'll put this at the origin, x0 equals 0. V0 also equals 0 because we just start pushing on it. Acceleration is 0.492 meters per second squared. We're pushing at 15 meters, so our final distance is equal to 15 meters. And we're trying to see how long that takes. Use one of our kinematics equation, x equals xo plus vot plus 1/2 at squared. xo is 0, v0 is 0, so x is 1/2 times a times t squared. T squared is 2 times x divided by a, so I brought my 2 over and my a down. T is going to be the square root of 2 times x divided by a. Can put my numbers in there. Square root of 2 times 15 meters divided by 0.492 meters per second squared. All that through the calculator, we should get 7.82 seconds. It's going to take just under 8 seconds to push our fridge across the floor. All right, so last, plot the friction force on the fridge as a function of the applied pushing force. So now this one is just conceptual. We have to think about how this works. So let's get ourselves an axis here. I'm going to put friction on the vertical. And I know we did this in class, but it never hurts to review it. So this is going to be our applied force. And let's think about what's happening with our pushing and our fridge. So as we just touch the fridge, we just barely touch it, our pushing force is 0. Static friction is going to match that pushing force, and it's going to be 0. We push a little harder, it still doesn't move, friction still increases to match the pushing force, and it will match until it gets to the maximum value. Static friction can never get bigger than its maximum value. So static friction will increase until it hits the maximum value, Fs max, where Fs max is equal to the coefficient of static friction times the normal force. Okay, so this is what's happening where it's not moving. This is static friction. And then as soon as our applied force, our pushing force, hits the static friction, as soon as it meets, it jumps. That's the threshold, that's where it switches. It jumps all of a sudden to kinetic friction. So it's going to lower because our coefficient is always smaller, and then no matter how hard we push on it, that kinetic friction will never change. Kinetic friction is always constant. So here's the place where it switches to kinetic friction. This is where it is moving. What we know about kinetic friction is that Fk is always less than Fs max. That's a feature of how these things work. And then to show that it's a sudden switch, it means these dots are perfectly vertically aligned. We often connect those with a vertical dashed line. So that's what the graph of friction as a function of pushing force will look like.